Welcome back, students and others. Let's take a look at component parts of a complex wave. As we've seen, complex waves, for example, in the bottom left of this image, are waves that have jaggedness. And we've seen that the fast Fourier transform identifies the component frequencies that are the formants, for example, of a vowel. Right? It identifies the component sine waves that are contributing to this complex wave. So for example, in the middle part of this diagram, if we took these three sine waves, or these pure tones, right, and combine them together, we'd end up with the complex wave on the bottom left of this diagram in red, the red wave right there, right? So the idea with the fast Fourier is you're going to try and separate out, identify what are the simple tones, or not the simple tones, the sine waves, the pure tones that go into creating this complex wave. And then on the bottom right of this screen, this diagram, we have a spectral slice that identifies the frequencies and their amplitudes. That is how loud they are, right? Amplitude. So this little blue peak right there is saying, hey, right here at this frequency, we have a lot of energy, acoustic energy right here. This is a resonance, right? Resonance of the vocal tract. And it's at this amplitude on the y-axis of this bottom right plot. And then the second component, or the second formant or resonance, right, is this one at this frequency, and it has this amplitude. And the third is back here, and it's at this frequency, it has this amplitude. Okay, so that's what we've seen before. This is a spectral slice that goes into a spectrogram, which is different than a spectral slice. And this is a waveform over here, and good. So my question is, well, can we kind of recreate a complex wave by just creating a handful of sine waves or simple, pure tones, putting them together and seeing how they sound? Do they approximate complex waves in the wild, right? In the wild, I mean, there's no place in nature where we hear sine waves, pure tones. We only hear it with a tuning fork. If you hit a tuning fork, you can hear a pure sine wave. Everything else is complex with all sorts of resonances. So let's jump over to our old friend Praat. Here's Praat. And I have a little recording here I just made. Listen to this.
E.
There is E, high front vowel, right?
Ah.
Ah, low central vowel.
Ooh.
Ooh, high back vowel. Okay, so what I've done is I've just gone into each of these and extracted out the center of those vowels. So here is E, like the center of that vowel. And then here, we'll just jump down to ooh for fun. Here's the center of ooh.
Ooh.
Okay, good. So what we could do, so we can say, hey, let's push this to a formant first. Let's go to analyze spectrum in the objects window of Praat, analyze spectrum, go down about 3/4 of the way to formant Berg, and pull it up on my other screen 1 second. Here it is. And because I'm an adult male, I'm going to say 5,000 hertz is the ceiling, and go ahead and go. It creates a formant object over here in the left part of my screen on the objects window. And I can come up to query, the query menu right there, and say, what is the mean F1? Let me pull it over to this screen. What is the mean F1 across E, my pronunciation of E? And it says 282 hertz is the mean F1. And I say, thank you. And then I can query the mean formant 2, or F2, and I get 2140 right there, etc. I can do that for the third and fourth formants. By the way, you can see those formants. Praat is trying to identify those formants with those red. Let me just zoom in a bit there. Right, these red dots down here, which actually are more visible if you zoom out a bit. Those red dots, which kind of form a line, are the formants. Praat is trying to identify the formants. So we have formant 1 at the very bottom, formant 2, formant 3, formant 4. And then above there, it kind of breaks up. It's kind of hard to identify. Okay, so good. We could do that by hand. And we could also get the amplitude of those frequencies. So if we take our sound E again and we say analyze spectrum to spectrum, and then it pulls it up over my other screen, bring it over here. I say, sure, go for it, fast Fourier transform. And then if I do query, and I say, give me the sound pressure level in decibels or dB. Sorry, I keep pulling up over this other screen. At 282. The first format was at 282. And it says that's at 49.7 decibels. Say, okay, thanks. And then I have that spectrum selected again. I go to query. And I say, what is the sound pressure level at 2140? Was the second formant frequency, right, in hertz. So I say, what is that? And it says 36.8 or 0.9. I can do that for the third and fourth formats. So I'm getting the frequency of the formats as well as their amplitude or loudness in decibels, right? And then I could create a pure tone. Let me create a new pure tone. I go up to new, sound, create sound as pure tone. And then we'll say, hey, we want the frequency to be, let me just say, call that demo. I want the frequency to be 282 hertz. And I want the, I need to change decibels into Pascal with a mathematical formula. I wonder if I can show you that mathematical formula real quick. It is right there. You take 0.0002, 4 zeros and a 2, times 10 raised to the dB divided by 20. So we had a dB of 49.7, I think it was, for the first format. We take 49.7 divided by 20, raise 10 to that, and then times it by 0.00002. That's 20 micropascal. Okay, so that's how you convert dB to decibels to pascals. And that's what Praat needs when you ask it to create a new sound. So when I do that, I get 0.00611, if I'm not mistaken, if my memory serves me. And if I click it, I get a pure tone. Let's look at it and listen to it. This is a pure tone. I'm using the word pure, but it's a sine wave. There you go. If we zoom in a bit, here it is. Right? It's a pure sine wave. And then I can do that for each of the other formats, taking into account their frequency as well as their amplitude in decibels, but convert it into pascals. Right, you can do this by hand like I've been doing in this little demo so far, or as you probably are aware, you can script this up. So let's take a look at this script. Let me show this as well, because it's gonna create some new objects. But in my script over here on the top right of my screen, I wonder if I can zoom in a bit for you. Well, we don't need to talk about the details too much here, but anyway, it extracts the first formants, that is, extracts the frequencies of the preponderance of acoustic energy, where the resonances are of the vocal tract, called formants. And then it also extracts the sound pressure level in decibels, and then it converts it into sound pressure units of pascals, and it creates sine waves. It creates 4 sine waves with the frequency and the sound pressure level of what my original vowel had after doing the fast Fourier transform. And then it combines those 4 sine waves into one. And we're going to see how much it sounds like my original E, A, U. I'll leave a link to this script in the description of this video. So anyway, number 1 here on the objects window is my original recording here with those 3 vowels. And then this one here, 147, is the E, right? And 148 is A, and 149 is U. Good. So we're going to loop over those identifiers, those ID numbers for those sound objects. And we're going to push it to a spectrum. We're going to push it to a format there. Then we're going to loop over 1 to 4 to get the first 4 formats. We get the current format there. After selecting the format, select the spectrum and get the closest peak, the nearest maximum, get the sound pressure level in decibels, convert it to Pascal, and then create a sine wave, a pure tone, using that frequency and that Pascal. Okay, so what we're going to do, I'm going to amplify it a little bit. It's a little bit quiet, so I'm going to amplify each of these. And yeah, it's going to create those sine waves at a sampling frequency or rate of 44,100, which is CD quality. Awesome. Good. Everything looks good. Let's go ahead and then we'll push it to a multi-track sound. Ready, set, go. There we are. It's finished all that work that I did by hand for all those sounds. I had to print out things here just so I can see that's working correctly. So yeah, there's 282. That's the first formant frequency. The dB was 49.7. Yep, there it is. It gets converted to a Pascal of 0.00611 or something. And then there is the second formant for E at 2140 hertz. Had a dB of 36 point almost 9. And that converts to a Pascal of that, etc. For each of the formants, for each of the vowels. Good. On the top left of my screen, let's look at what was created over here. So it did all that work I was doing by hand earlier. Here are the pure tones. It's like if I just open this up and look at it, here is a pure tone that's approximating the first formant of my E. Let's just listen to the visible part. Okay, so that's just a pure tone. The amplitude in pascals right here where I'm cursed on the top left of my screen where I'm circling is 0.0611. I amplified it by 10 to make it louder for us. And the frequency is not listed right here right now, but it was 282. Here's the second one. If we just look at that real quick. Yep, this is a sine wave. We just zoom in a bit so we can see it a little bit clearer. Yep. Sine wave, amplitude's that on the top left of my screen. Those numbers are corresponding to what I had to print out over here. And the frequencies as well. Okay, so the take-home message is if we come down here to this combined wave, we take these four pure tones that were trying to approximate each of the four formants that were in my E, and we look at it. Let's take a look here. Let's just zoom in a bit so you can see that these indeed are pure tones. Let me go back over here and zoom in on that. Yeah, so the top one is the first formant pure tone, or trying to approximate the first formant pure tone. The second tier there is the second, third, fourth, etc., with their differing amplitudes or loudness, right? So if we back out and listen to this thing, listen. Okay. It doesn't sound like a human, but it sounds somewhat like E. Okay, let's listen to the second one, which was Ah. Again, just taking these pure tones that we're trying to approximate each of the formants in my Ah. This is what we get. Let's take a look up here. And what do we see here? Let me just zoom in so we can take a look. Yep, here we have different kind of amplitudes and frequencies of the different formats. And if we zoom out and listen to all of it, it sounds very robotic, does not sound like a human, but it's trying to approximate Ah. And then the last one is Ooh. Again, just to be super clear, we're looking at pure tones that are being played together. And let's just listen. Okay, so again, it's robotic. It doesn't sound human, but I think you can hear that the first one sounds like E. I'll just play it. Listen to this. Second one sounds somewhat like Ah. Maybe less so than the others. And this one should sound like Ooh. Again, I'm trying to recreate those vowels with just the first four formants as sine waves, pure tones. Yeah, so that's pretty cool. At least I think it's pretty cool that you can do that. Now, we don't have all the information in there. That's why it doesn't sound fully like a human saying E, Ah, Ooh. But just taking the first four formats does a lot. So there you have it. Cool stuff, playing with waves, sound waves, and sine waves, making complex waves. Thanks for watching. See you next time.